Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Welcome to the Vacuum Technology and Process Application course, Module 1, Lecture 3. In this lecture, we will be covering the kinetic aspects of gases and certain physical parameters, and based on which how do you classify various regions of vacuum. This is very important because different ranges of vacuum are meant for different applications, and in different ranges the physical parameters come in different style. For example, pure vacuum, there will be viscosity term, there will be viscous drag, it behaves like gases, etc. But as you go towards high and higher vacuums, there will be molecular pictures, it will not be a gas flow. So, in any way, the kinetic theory of gases is very important background, which all of you should have some knowledge when you are dealing with this rarefied pressures, rarefied gases. In fact, kinetic theory of gases deals with ideal gases, and you will be surprised to see that ideal gas theory is ideally valid for vacuum technology, because that is where the number of molecules are less compared to the dimension of the chamber, and you can say that the size of the particle is much less compared to the distances they travel between collisions, etc. So, most of the assumptions that we make in kinetic theory of gases are really valid at low pressures. That way, the famous equation P v is equal to nRT is ideally valid for vacuum technology. So, these theory of kinetic aspects of gases at rarefied pressures we will be just touching. I am not going to the detailed derivations of it, because you can find them in several books. This is a good old theory and a well established theory. It is the basis for various other things like thermodynamics or mechanical engineering or basic gas physics, gas dynamics. So, kinetic theory of gases is a very well developed theory, and it deals with molecular speeds, it deals with several parameters on molecular level, also relating it to the gas level, which I do not have to explain to you, because it is even covered in 11th and 12th class of school days. Okay. So, within this kinetic theory, I will cover the speeds, molecular speeds at various pressures, and associated with them how several physical parameters of vacuum vary, and with those parameters we will try to classify the regions of vacuum and then link it to different process applications. Okay. Now, look at the curve. This is of course very friendly to most of you. The very famous people Maxwell and Boltzmann, they developed theory of gases, theory of velocities, of distribution of velocities of a gas at any temperature, and we need to understand this a little bit. I am not going to the detail of that whole curve or anything. It is a statistical thermodynamics or statistical mechanics, where Maxwell and Boltzmann gave a lot of ideas which are valid for various theories which came later. So, what they have done is there is a distribution of velocities. If you carefully observe the curve at any temperature in a given ensemble of molecules, there will be distribution of velocities. The y axis is number of such molecules with that particular velocity, and x axis is the velocity. So, at any instant of time, the gas inside a box will have all these velocities. and it will reach a peak at a particular velocity, that is called most probable speed. It will also have an average velocity, which is V average, and that is very useful concept for most of the calculations in molecular flow in vacuum technology. We also have mean square velocity. So, all these three velocities are well explained in any book on kinetic theory of gases. But for vacuum technology, we will be more interested in average velocity. That comes again and again in pumping speed calculations or throughput concepts and cryopumping aspects like that. We also know that this velocity is strictly depends on the type of molecule that we are considering, whether it is a nitrogen gas or oxygen gas. It also depends on the temperature. So, if you look at the equations in the right side, mostly it contains capital T and small m. K is the Boltzmann constant and pi and other things are all standard constants. So, most of these velocities depend on temperature and mass, nothing else. So, even under rarefied conditions where pressure is less, the distribution of the velocities will be same, but the value of the number at any particular velocity, that may be less, because total number of molecules are less. So, area may be different, but the distribution is more or less similar. But when it comes to the temperature, it is quite a strong function of temperature, all these three velocities. Okay. Now, if you right side, if you observe, you will find three equations. The most probable speed that comes at the peak is given by root of 2 kT by m. This is derived from kinetic aspects. You can easily derive starting from various statistical criteria and solid angle suspended by molecules, etc., etc. There is a long derivation for every equation, which is very interesting. For the sake of it, students can go through the book on kinetic theory of gases. The average velocity, which is very useful for our vacuum technology course, is root 8 kT by pi m. The mean square velocity, the squared velocity, is given by 3 kT by m. Okay. This average velocity at room temperature is of very high extreme importance to vacuum technologies, because vacuum technology day to day life, we have room temperature chambers, we have air containing nitrogen, oxygen, hydrogen, helium, etc. But different gas molecules within the mixture will have different velocities, because their m is different, their t is different. So, I have given few values, characteristic values, average velocity values at room temperature. If it is nitrogen gas, it is 480 meters per second. If it is oxygen gas, 450 meters per second. If it is water molecule, 600 meters per second. If it is a very light molecule like hydrogen, it is going to be 1.8 kilometers per second. All of them are more than a typical speed of sound in air, which is a popular number, 330 meters per second. What is this velocity? It is not the gas velocity, it is the average molecular velocity, because molecules are under random motion. They hit each other after certain distance, which we will see, we will call it as a mean free path. And at the instant of hitting, it is an elastic collision, and it comes to stop and immediately gets reflected or deflected, and it keeps on going. So, this motion is a random motion. Right now, here the molecules are randomly moving and they are hitting each other. Okay. And when they hit, how much distance they will travel between two successive hits, how much flux is there on wall per unit area, and how much time is required to make a monolayer. All these things can be worked out in detail with some derivations, but that is not our lookout. I will give you the number values and some expressions for it also as we go forward. But what is this velocity? This velocity is the random velocity between two collisions, and sometimes people call it as random velocity, sometimes they call it as average velocity, and sometimes they call it as thermal velocity, because it is associated with the temperature of the gas. If temperature is different, this average velocity will be different. Okay. But if the pressure is different, pressure is low, with this average velocity it will travel longer path, but average velocity will be strictly function of temperature and molecular weight. When we say velocity, that we use it in Reynolds number rho v d by mu, that velocity is different. That velocity is the uniform velocity of the entire gas. That is much less compared to this, even under extremely turbulent conditions, or when the flow is turbulent flow or laminar flow, the velocities are maximum 20 meter per second or 100 meter per second maximum. So, it is that the velocities are real gas velocities. When you observe at a particular point the velocity of the stream, that is that gas velocity. This particular random velocity or average velocity is between two collisions, even in static picture, even there is no flow, even then this velocity is there, is associated with the thermal energy that it contains, and these velocities can be extremely small only at very low temperatures called cryogenic temperatures. In fact, these velocities are creating force on a wall, near the wall. In fact, these velocities are related to pressure. You might have seen in your class days 1/3 mnc square bar. It is that velocity that is again coming here. It is not the gas velocity which we talk in fluid mechanics. Why I am stressing this point again and again is this average velocity comes into picture again when we deal with turbomolecular pumps. When we deal with cryo pumps, for example, at various temperatures, the velocities will be different. So, molecule going in a chamber towards the pump, cryo pump, will have one velocity. When it touches that surface and comes back, it will have another velocity. So, these random velocities which are related to pressure, etc., they are also functions of temperature. So, accordingly we will have to work out pumping speed expressions and throughput expressions using these velocities only. We will come to that point later when we deal with production, measurement, troubleshooting, etc. So, the importance of this average velocity comes in pressure measurements as well as pumping mechanisms, the flux, even in thin film depositions, the rate of depositions, for example, all of them can be related to this velocity and associated parameters like mean free path, time to form monolayer, number density of molecules, etc. Okay. We will deal with all these physical parameters in the next slide. So, in this one slide, though I am telling again and again same concepts, but it is important for you to know this velocity, average velocity is the random velocity. It keeps on changing and it is averaged value of that velocities. Now, take a small cubical box, lots of molecules are there. I am not showing millions of molecules, but actually at atmospheric pressure you have 2.5 into 10 to the power of 19 molecules per unit volume, that is centimeter by centimeter by centimeter. That cube will have 2.5 into 10 to the power 19 molecules. Here I am only showing a characteristic figure. So, the number of molecules per unit volume is what is known as molecular density. What will happen at lower pressures? Naturally, number will be less and it will be strictly linear functioning, because same P can be told 1/3 mnc square bar, P can be told in mechanical engineering force by area, P also can be told NKT, that N is the number density and KT is the thermal energy. So, in a way it can be called all these thermal parameters. But molecular density is also a function of pressure, and it is a linear function of pressure. If only these molecules are not moving randomly, and if they are moving in a particular direction, as time passes, what will happen? The ground floor will have all the molecules because of gravitational force, and first floor may not have molecules. This kinetic theory is giving us a very clear picture why molecular density is more or less uniform. It keeps on changing as you go up in the altitude, but in a slow manner, but within a short distances we will not feel any variation. The number density in that corner is same as number density here, that they get readjusted. All these concepts are thoroughly discussed in kinetic theory of gases. So, right now what we are interested in vacuum technology is molecular density. It is the average number of molecules per unit volume. Second concept or second physical parameter that we are interested is mean free path, which I already discussed in the earlier slide. It is the average distance that a molecule travels between two successive collisions of its own. So, when molecules are moving randomly, that molecule is coming, this molecule is going, they may hit, because by the time it comes here, it may go this way. So, it is not the distance between the molecules, it is the average distance a molecule freely travels between two successive collisions. That is why it is called mean free path between two collisions, and that distance may be different with two various collisions. So, you will have to take again average, just like we have taken average velocity, here we will take average distance. Okay. It is somewhat like in a crowded room, some 10 boys are moving, they may not hit with each other, but if at any instant of time if you take a picture, the distance between two boys is very small, 1 or 2 meters, but they can randomly move without hitting each other for even 1 kilometer. Okay. So, this average distance that a molecule travels between two successive collisions is called mean free path. It is given by an expression as 1 by root 2 pi d square n. Okay. N should be pi d square n, it should be in the denominator. So, the equation that I have written, little typing error, the pi d square n also comes in the bottom, 1 by root 2 n pi d square. So, d is the diameter of the molecule. Now, if you look at the picture, what is happening? Molecules hit each other, they travel different lengths at different instants of time. So, you can see an average distance, you can easily figure it out from here. A pictorial representation I have given here. What will happen to this mean free path at low pressures now? Number of molecules themselves are going down as per the molecular density concept here, which is proportional to pressure. Now, the pressure comes down 100 times. So, mean free path will increase 100 times, because less number of molecules are there to collide. On an average, longer path it will travel with a standard average velocity. There are good derivative steps for this, and we can appreciate it is interesting to derive mean free path as a function of molecular diameter, etc. It is available in Wikipedia and many books also. I suggest students to go through that and work out this equation. So, third concept is collision frequency. So, number of molecules here randomly moving, when they go towards the edge of the chamber, that means chamber wall, there they will be colliding at a particular frequency, number of molecules per unit area. This is of course related to force, and force per unit area can be related to pressure. This way also derivations are there in the school days for pressure. So, we are interested in this surface collision frequency not to understand fundamental concepts of pressure and all. We are interested in this surface collision frequency because this is the one that is going to control the rate of deposition in thin film coatings, which is a fundamental for semiconducting devices, etc., metal coatings, etc. There we will again come into this concept surface collision frequency, which is given by n molecular density, and nu bar is the average velocity divided by 4. The fourth concept or fourth physical parameter that we are getting when we deal with vacuum technology is time to form a monolayer. If I keep a substance here, immediately lots of gas molecules are falling on it and it forms a monolayer if it sticks to that surface. So, at any instant of time, for example, if you keep some gold, fresh gold piece, after some time it become dull. That means a lot of layers got absorbed. Again when you clean it will be shiny. So, but within few seconds again it will be, first layer will be formed, but second layer will take a lot of time. Okay. But we still see the shininess because first layer is so thin, optically we can see the shine. But if you are interested in knowing how much time it takes to make the monolayer of the molecules here on any solid surface, that is known as time to form monolayer. This is also very important in thin film technology and vacuum technology, particularly in electronic industries. So, this is given as tau and the equation for it is 3.2 into 10 power minus 6 by P, where tau is in seconds and P is in millibar. So, we have covered 4 concepts: molecular density, mean free path, surface collision frequency, time to form monolayer. There are many other concepts in kinetic theory. We have taken these concepts with which we can classify the ranges of vacuum. So, by analyzing the values of n, molecular density, lambda, mean free path, tau, time to form a monolayer, and the characteristic dimension d, which is nothing but average distance, average dimension of the chamber within which we are discussing a particular application. That means, comparing these things lambda and d, we can have different ranges of vacuum. Low vacuum, for example, poor vacuum, that means high pressure. That is subdivided into 2 small ranges for convenience, 760 to 0.5 tar. What is tar? We will come later. That is 1 millimeter of mercury. Units we have just now discussed, but again in measurement chapter we will be going into detail of it. For the present, you think 760 tar is the atmosphere, 760 to 0.5 tar is called medium vacuum, and 0.5 to 10 power minus 2 tar, 0.5 to 10 power minus 2 tar is called medium vacuum, and 760 to 0.5 tar is called low vacuum. This low vacuum, the molecules behave like gases because density is quite high, just quite small, little bit less compared to atmosphere, but still the molecules will have a continuum concept. That means, whatever happens to one molecule, it will impart that to the other molecule. There is an interaction, there are shear forces, there are continuum concepts in the gas. So, when you try to drag some molecule, it will try to drag the other molecule. So, these drag forces will be there. So, all these forces will cease to exist once you come to 0.5 tar. But still it is called medium vacuum because there are certain continuum concepts and certain molecular concepts. So, all this range of 760 to 10 power minus 2 tar is called low vacuum. Why we call low vacuum? It is normally useful for not very high tech applications, for mechanical applications and chemical applications and pharmaceutical applications, where we need forces also. We also need drying, we also need typical thermodynamic aspects to happen. So, all those things like boiling point reduction with pressure, all these concepts are there as in gas physics. So, those concepts are valid for this low vacuum. And in low vacuum, the lambda, the mean free path of the molecules just now we discussed, is so small because number of molecules are quite large. Each molecule travels only few microns of distance before they hit another molecule. For example, at atmospheric pressure, the molecules are hitting after every 7 to 8 microns distance, it is hitting. So, within 6 to 7 microns, if it is a helium molecule or hydrogen molecule, it is going 1800 meters per second, or if it is nitrogen molecule, some 450 type. So, that is should be understood like that. In high vacuum, that is starting from 10 power minus 3 to 10 power minus 7 tar, we get a situation where the mean free path is longer compared to the dimensions of the chamber. That means molecules are freely moving, they hit the wall first before they hit another molecule, because very few molecules are there. The chance of all of them are randomly moving with an average velocity, and that velocities are also distributed velocities. We take average velocity for mathematical calculations. So, when these distributed velocities molecules are going in the 3D, they may not hit each other, but they will definitely hit the wall, because it cannot go out of the chamber. So, a situation will come where molecules moving with that average velocity, which is defined by the temperature of the chamber and gas, these velocities are such that these mean free paths are such that collisions with the wall are dominating compared to the intermolecular collisions. When they do not collide with each other, there is no concept of viscosity. Viscosity gives the drag, shear drag. If that is not there, concept of Reynolds number, viscosity, gas physics, laminar flow, all this is not there. In fact, in vacuum technology, when you are trying to reduce pressure, first few seconds there will be turbulent flow, next few minutes there will be laminar flow. Once you start coming to a pressure value of below 1 torr, it is all molecular flows. So, we can forget about all these aspects related to gas physics or equations related to viscosity, etc. in the after 2-3 orders of vacuum, which are very much required for metallurgy, space technology, nuclear, electronics, etc. So, that physics is totally statistical physics. If you want to understand the growth rate of a thin film, or growth rate or particle, how it is moving in a particle accelerator, or space technology, what is happening. If you want to understand, we do not have to go to the gas dynamics, we have to only see the statistical mechanism. So, here in the high vacuum region, the gas molecules in the chamber move sufficiently long path, but that path is longer than the actual chamber dimension. So, most of it will be colliding. Once in a while they collide with each other. So, lambda is much more compared to d. After lots of collisions with the chamber wall, finally it may collide. So, d may be few meters, but this can be hundreds of meters, lambda can be hundreds of meters. If you go to still better vacuums called ultra high vacuum, which is important for space technology, nuclear and electronics. High vacuum is important for metallurgy, vacuum distillations, little bit molecular distillations, not normal distillation. So, ultra high vacuum is another phenomena by itself, another physics by itself. There, time to form monolayer is also very important. Impurity should not be there. For scanning electron microscopy, you are seeing the surface analysis. Before that, a foreign impurity layer falls on that few micron layer, then we will not get the information about the interfaces in biomolecules, etc. When you are studying surfaces and interfaces, you cannot allow foreign molecules to form a monolayer. So, the tau should be a few hours, and your observation time in understanding some structural things or so topology, etc. is in few minutes. So, you will get a correct picture. That is why most of the analytical instruments, SEM, X-ray, XPS and TEM, most of them are working at ultra high vacuum conditions. And you will etch first initially, put a fresh cleaved surface and try to understand its surface and relate it to various parameters in metallurgy or biotechnology. So, this is very important in ultra high vacuum. And what is happening to lambda here? Lambda is kilometers, because they will never hit each other, very few molecules, but most of them will hit the chamber definitely. So, lambda is much more compared to d. So, when you say lambda is much less than d, d is the characteristic dimension of the chamber, it is called low vacuum. Lambda is of the order of d and little more than d, typical metallurgy and molecular distillation type of works or cryogenic insulation works, etc. It is called high vacuum. And when you go to electronics and nuclear technology and space physics, etc., we come into all the analytical instruments dealing with surface analysis, which are very important in metallurgy and material science and also the biotechnology, etc. These ultra high vacuum based instruments are there. So, if you go next time to the laboratory, most of the electron microscope, etc., backside there will be high vacuum turbomolecular pumps, ultra high vacuum, and higher the vacuum, clarity of the picture will be high. So, we will get into 3 ranges called low, high and ultra high, depending on the relative variation of lambda and compared to characteristic dimension. Now, let us look at the table. It gives the typical values of lambda, d and tau and collisional frequency at various pressure values. And I have given lower limit of rough vacuum. That lower limit will become the higher limit to the next high vacuum, like that, and atmospheric pressure is 760 torr. So, I have given typical values of lambda, tau and also the collisional frequency as well as mean free path and number density at various pressures that we encounter in vacuum technology for different applications, 10 power minus 3, minus 6, minus 9, minus 12. These are all torr. 760 torr is the atmosphere. You will see number density is gradually going down, and 10 to the power 19 molecules into 2.7 at atmosphere. When you go to ultra high vacuum that we regularly use in our day to day life in high tech, it is very high, sorry, very low, 3.5 into 10 to the power of, I think it is 4. Okay. So, roughly 35,000 molecules are there even at 10 to the power of minus 12 torr. But it will take roughly 2.5 into 10 to the power of 6 seconds. That means almost few days it will take to form a impurity layer. So, you can very nicely study the surfaces and interfaces. You can very nicely prepare pure layers, interfaces which are required for electronic industry, space technology, nuclear. A high vacuum, for example, it is coming out to be the monolayer formation will be less naturally, mean free path will be longer compared to atmosphere, but shorter compared to the ultra high vacuum. So, when you look at the number density, it is linearly coming down, mean free path is linearly going up proportionately, and time to form monolayer also goes up. So, these concepts what I have explained so far, mean free path, time to form monolayer, surface collisional frequency for the deposition rate measurements, etc., and molecular density, which will give various other parameters like insulation, thermal insulation, electrical insulation, breakdown voltages in interrupters, or thermos flask, what is the heat transfer. There are two heat transfers, one is convection and residual gas conduction, both are related to the number density. Radiation is independent of medium, and conduction through the walls is that is a solid state conduction. So, in vacuum technology, these three parameters are going to play an important role, and these three regions have to be understood in terms of these physical parameters, and they will have applications for various varieties of applications, low tech or high tech or ultra high tech. Thank you very much. With this idea of various ranges, you get a feel of the regions of vacuum. Thank you.